Hello, in this video we're going to look at linear transformations from Rn to Rm. So we're going to say what linear transformations are, and this will probably just be one of several videos on linear transformations because there's a lot to say about them. But linear transformations are a type of function, and they're a type of function that satisfies a key property called the linearity property. And to introduce linear transformations, let's recall this fact about matrix vector multiplication. So if you have a matrix A, if you have a matrix A, every matrix, an m by n matrix A, we can think of it as taking vectors in Rn to vectors in Rm by multiplication, right? If you have a vector x in Rn, then if you do A times x, you get a vector in Rm. So every matrix, every m by n matrix, well, a matrix is just a block of numbers, basically. It's just a bunch of numbers in a box. But when we're thinking of A taking vectors to vectors, an input vector x goes to the output vector A times x. When we have something that takes inputs to outputs, that's a function, right? So every matrix gives a function. So it gives rise to a function. And to distinguish that from the actual matrix, because the function isn't the same as the actual matrix, literally speaking, I'll call the function t sub a. So a is a subscript, and this is a function from Rn into Rm. So I'm using this notation where this is like the function notation where first you say the name of the function's called t sub a, and then you have a colon, and then you say the domain. So where are all the inputs are in Rn, right? So this is the domain of the function. And then you say it goes to, so that's the arrow, and then where the outputs are in Rm. So that's called the codomain or the target. Okay? And what is this function? It's a function, it's defined to be the function that takes x to ax, a times x. So let's just recall that this a times x, I'm doing a matrix times a vector, right? On the left-hand side, what is this t sub a with the parentheses x? This I'm using the function notation. Right, just like if you have a function f and you plug in x, you get f of x, right? That's the same thing that I have here. So I have a different notation. Here I'm thinking of plugging in x into the function t sub a, and then on the right I have an actual matrix times a vector. So x is a vector in Rn, and then the output is an element of Rm, right? So for instance, if you have a 3 by 2 matrix, and let's say these are the entries, A, B, C, D, E, F, this is going to take you, what's the domain of the T sub A? If I can do A times X, or X is a vector, how many components does my X have? It has 2, right? Because I have to be able to multiply. In order to be able to do A times X, I have to have 2 components in X. So my domain is going to be R2. So I have like a vector X, say here. And then the output is going to be in R what? So here's R2, and then the codomain is R. If you do A times a vector, the output is going to be in R3, right? if I do A times a vector, I will get a vector with 3 components. So I have a vector in R3. So my codomain is R3. So it's taking vectors in R2 and spitting out vectors in R3. So I don't know what my AX will look like. Maybe it's this. Who knows? I mean, it's going to depend on what A is. So now I have this function that sends x to AX. But this function isn't just any function. It actually satisfies an important property. So recall that it's one of the properties of matrix vector multiplication that whenever you take 2 inputs, so for any vectors v1 and v2 elements in Rn, if I add them, if I add them, I get v1 plus v2. And if you take your matrix A and you multiply by v1 plus v2, what are you going to get? You're going to get A times v1 plus A times v2. Okay, so it might be a good idea to review why that's true. And then another property is, so also, sorry, there's like an announcement outside, I'm not sure what that's about. Anyway, so whenever you have a scalar C, and a vector V in Rn, so a scalar C is a real number, C is an element of the real numbers, and a vector V, well, you can take CV, and then if you do A times it, what are you going to get? You're going to get C times the vector AV. So in other words, you can take A times V and then multiply that by C. Right, so let's just call those 1 and 2. So in terms of what that says about the function T sub A, what that's saying is that T sub A of V1 plus V2 is going to equal T sub A of V1 plus T sub A of V2. And well, that's the first thing. And then in terms of the second thing, if you plug in C times V into your function, you're going to get C times T of V, T sub A of V. Okay. So let's just call that 1, and let's just call this 2. And it's really important that these equations are true no matter what your V1 and V2 are, right? It's for any V1 and V2 in Rn. It's not that this equation is sometimes true, it's that it's always true, no matter what your V1 and V2 are, as long as they're in the domain. And similarly for the second one, it's for every scalar C and for every vector V in Rn, the second equation is true. Again, it's not that sometimes the thing on the left matches the thing on the right, it's that every single time the thing on the left matches the thing on the right. And similarly for these two, right? These two equations are true no matter what your V1 and V2 are, as long as they're in the domain, and it doesn't matter what C is, as long as it's a real number, and then it doesn't matter what V is, as long as it's in the domain. This equation is always true. And so this leads us to the definition of a linear transformation. Basically, a linear transformation is a function that makes these two equations true. So, definition. A linear transformation by the way, sometimes instead of the word transformation, the word map is used or the word mapping. They all mean the same thing. So a linear transformation /map/mapping, for me, I'll use linear transformation from Rn into Rm is a function, say t. Okay, so t is a function that has inputs in Rn and the outputs are in Rm, satisfying these properties, which I'm gonna spell out. So the first property is that for any, so for all v1 and v2, by the way, for any, for all, and for every, they all mean the same thing. Okay. For all v1 and v2 in Rn, t of v1 plus v2 equals t of v1 plus t of v2. And then the second thing that it has to satisfy is that for all scalars c and all vectors v in Rn, if you do cv and then plug that into t, so that's t of cv and get the output, that's c times t of v. All right. So any function that satisfies both these properties, that's called a linear transformation. And let's just clarify that what's going on here. So in this first condition, v1 plus v2, this is in Rn, okay? And this addition, this plus here, this is in Rn, in Rm, because t of v1, this is a vector in Rm, this is a vector in Rm, and when you add them, well, you know, we're talking about Rm here. Okay? So hopefully that clarifies the notation. And similarly, this CV, right, this is happening in Rn, and then this C times T of V, that's happening in Rm. Like I have T of V is a vector in Rm, and so C times this is in Rm. Okay. And so therefore what we've shown is that every T sub A, so for instance, every T sub A is a linear transformation. Actually, it turns out that every linear transformation from Rn to Rm has an associated matrix A. So actually, it turns out that all the linear transformations from Rn to Rm is going to be a TA, T sub A for some matrix A. So then that leads to the question, well, why do we care about linear transformations if, you know, if every linear transformation is just coming from a matrix? And the reason is that we will, in linear algebra, we're going to be interested in more general linear transformations than just from Rn to Rm. So in this video, we're just looking at linear transformations where the domain is Rn and the codomain is Rm. But when we talk about subspaces, we're going to want to talk about linear transformations from one subspace to another subspace, and you can't do that using matrices. So this stuff about linear transformations, they all come from a matrix. That's only true when your domain is Rn and your codomain is Rm. Okay. So this isn't all there is to say about linear transformations. This is just like an introduction. We're looking at a very specific type of linear transformation. Anyway, let's just look at some examples. So for instance, let's say that t is the function that takes x1 and x2 to x1 minus 3x2 comma 2x1. Okay, by the way, I should probably say something about the notation. So when we have a linear transformation that's taking Rn to Rm, we often think of the perspective of Rn and Rm as being points instead of vectors. So here what this is saying is that if you plug in the point x1, x2, you get this point x1 minus 3x2 comma 2x1. And okay, yes, you might also notice that technically, since the ordered pair is x1, x2, really there should be parentheses here, because your x1, x2 in the parentheses, that's the thing you're plugging in, and then you have this parentheses, this other parentheses for the function notation. But often we just omit one of the parentheses because it looks kind of weird to have two kind of like double parentheses like this. So usually we just write it like this. Okay. So this is the result of plugging x1, x2 into the function t. You get that output. So I see that t is a function from r what to r what. Well, I see that the inputs, I have two numbers, right? And so I have a function from r2 to what? Well, again, I see two outputs, right? Well, technically this is a single output, but it has two components. The first component is x1 minus 3x2, the second component is 2x1. So this is a function whose outputs are also in R2. Okay, so that's the function t, and then the question is, show that t is a linear transformation. So how do we do that? Well, what we need to do, right, to show that something is a linear transformation is to show that these two properties are satisfied. The first property is that for all v1 and v2 in Rn, you have this equation. And then the second property is that for all c and all v, t of cv is c times t of v. So what you actually need to do is you need to start out, let's do the first one. We need to show that for all v1 and v2 in R, well, in this case we have R2, right? So let's just write out what the first thing is. We need to show that for all v1 and v2 in R2, t of v1 plus v2 is equal to t of v1 plus t of v2. So what we're going to do is we're actually going to calculate t of v1 plus v2 and then t of v1 plus t of v2 and then show that you get the same thing. And to do that, you have to work with coordinates, or you have to work with the components of v1 and v2. So first of all, we start off with two vectors in R2, v1 and v2. So the first step in the proof is to say let v1 and v2 be elements, okay, or we could just say be vectors in R2. Well, v1 is going to have components and v2 is going to have components. So we need to introduce notation for those. So suppose that v1 is x1, x2, and the vector v2 is going to be y1, y2. Sure. So now we calculate the left-hand side. Okay, t of v1 plus v2. Well, first we need to figure out what v1 plus v2 is. So v1 plus v2 is going to be, the first component is x1 plus y1, and then the second component is x2 plus y2. So then you have that. And so t, what's t of v1 plus v2? Well, that's going to be t of x1 plus y1, comma, x2 plus y2. And what's that going to be? Well, now we need to use the definition of t, right? In this problem, you're told what t does to your vector. Now notice that here, okay, so when you're looking at this, in this notation, your x1 and x2 are the first and second components of the vector. So what this is saying is that you take the first component, okay, so the output of t, right, there's two components to this. The first one is x1 minus 3x2, the second is 2 times x1. So what this is saying is that if you have an input, it has a first and second component, x1 and x2. Okay, what does t do to it? The first component of t is x1 minus 3x2. In other words, you take the first component and then subtract 3 times the second component of your input. And this is going to give you the first component of the output. And to find the second component of the output, that's 2 times x1, you multiply 2 by the first component of the input. That's what this is saying. So in this case, so let's just write that down, the formula again, so I don't have to keep scrolling up. It's tx1, x2 is x1 minus 3x2, comma 2x1. Well, in this case, my inputs are x1 plus y1, comma x2 plus y2. Those are my components of the input vector. And so the x1 and x2 in this formula, this one is the x1 and then that one's the x2, right? I'm using different symbols for the x1 and x2. So what am I going to get when I do this? I'm going to get the first component. So the first component is x1 plus y1, and then minus 3 times the second component. The second component is x2 plus y2. Okay. And then I have comma 2 times the first component. So my first component is x1 plus y1, so I'm going to get 2 times x1 plus y1. It's definitely important to be able to do this because, you know, it might sound confusing, but it is important to be able to do this. So let's see what you get when you simplify. This is going to be x1 plus y1 minus 3x2 minus 3y2, comma 2x1 plus 2y1. So now we calculated t of v1 plus v2. Now what we need to find is t of v1 plus t of v2. Well, t of v1, that's going to be t of x1 comma x2 and what that's going to be is x1 minus 3x2 comma 2x1. And t of v2, that's t of, so remember we let v1 be x1, x2, and v2 be y1, y2, right? So this is t of y1, y2, and then by definition, this is going to be y1 minus 3y2, comma 2y1. So what do you get when you do t of v1 plus t of v2? You're going to get this plus that. And to add those two vectors together, you add the components together, you get x1 plus y1 minus 3x2 minus 3y2, comma 2x1 plus 2y1. And now we calculated t of v1 plus v2. We got this. And we calculated t of v1 plus t of v2. And what do you notice? We got the same thing. So therefore, t of v1 plus v2 is in fact equal to t of v1 plus t of v2. And that's the first condition that we needed to check. All right? Now we still have, so that was the first condition out of two. Now we also have the second condition. So the second condition says, suppose that we have C a real number, so we write let C be a real number, and let V be a vector in Rn. Well, in this case, that's R2. So we need to check that T of CV is equal to C times T of V. And again, we calculate each side and check that you get the same thing. So we need to use coordinates, the components of V. So suppose that V is x1, x2. Okay. Then, okay, let's calculate the left-hand side. Well, CV is going to be C times the vector x1, x2. And that's going to be, what? What are the components? C times x1 and C times x2. Now we plug that into T. So T of, now I'm switching back to the notation of plugging in the point. T of Cx1 comma Cx2, that's going to be, now we need the formula for T again. Let's see if I can move that down here. So my input has first component Cx1 and Cx2. And so, well, it'll probably be a good idea if you pause the video and write down what you get and then check the answer. All right, let's go over the answer. So this is going to be, I take the first component, that's Cx1, that goes in here. That goes into the x1 there. So that's going to be C times x1 and then minus 3 times the second component, which is C times x2. And then comma 2 times the first component, which is Cx1. Okay. So that's T of CV. Now I need to calculate C times T of V. So also C times T of V is going to be C times T of x1, x2. And that's C times the vector x1 minus 3x2 comma 2x1. And this is going to be, we can multiply the C across, C times x1 minus 3cx2 comma 2cx1. Because remember, when you take a vector and you take this vector and then scale it by a scalar, you multiply each component by that scalar. And now what do you notice? We calculated T of CV and you got that, and we calculated C times T of V and you got that. And are they the same? Yes, they are in fact the same. So notice that we have T of CV equals C times T of V. And that shows the second condition is true. And since the first and second conditions is true, we conclude that therefore T is a linear transformation. Okay? So that's the proof. That's how you prove using the definition that a function is a linear transformation. It's time consuming, but the process is actually pretty straightforward. You need to show that the two conditions of being a linear transformation are satisfied. And to do that, to show number one, it always starts off with let v1 and v2 be in Rn, and then in this case, since you're given t, you're given the formula for t in terms of the coordinates, in terms of the components, you want to work with the components of your v1 and v2. And then similarly for number two, the second condition. So that's how you check that something is a linear transformation. And we're going to learn some theorems that we can use instead, but this is how you would check it directly from the definition. Okay, let's think about what it would mean to not be a linear transformation. So we're done with that example. What does it mean for a function to not be a linear transformation? So a function t from Rn to Rm is not a linear transformation if well, let's think about this logically. To be a linear transformation, you have to be a function that satisfies both properties 1 and 2, right? So anything that doesn't satisfy both 1 and 2, that's not going to be a linear transformation. And so what does that mean, to not satisfy both of them? It means that at least one of these properties is not satisfied, right? So any function that doesn't satisfy property 1 or doesn't satisfy property 2, those are going to be the functions that are not linear transformations. So now let's break that down even more. What does it mean to not satisfy this first property? The first property says that every single time you have two vectors in Rn, that the equation is true. The left-hand side equals the right-hand side. So to not do that, it would mean that there are v1 and v2. There exist vectors v1 and v2 such that the left-hand side is not equal to the right-hand side. There's at least one instance where the left-hand side is not equal to the right-hand side. That's what it means for the first property to not hold. So let's write that down. If either, okay, let's use bullet points. There are two vectors v1 and v2 in Rn such that t of v1 plus v2 is not equal to t of v1 plus t of v2. That's what it would mean for the first condition to not be satisfied. But remember, to not be a linear transformation, it's either the first or the second. So you either need that there are two vectors v1 and v2 such that t of v1 plus v2 is not t of v1 plus t of v2, or excuse me, or the second condition is not satisfied. So let's go back to the second condition. The second condition is that whenever you have a real number, c, and a vector v, t of cv is equal to c times t of v every single time. So what it means to not have that is that it's possible for this left-hand side to not be the right-hand side. There's at least one instance where the left-hand side and right-hand side do not match. That's what it means for the second property to not be true. So what that means is that there exists there is a scalar C and a vector V in Rn such that the left-hand side does not match. So T of CV does not equal C times T of V. So that's what it means for a function to not be a linear transformation. So if you can find two vectors v1 and v2, two input vectors, such that this left-hand side doesn't equal the right-hand side, then you have a function as not a linear transformation. Alternatively, if you find a scalar c and the vector v such that the left and right-hand sides here don't match, okay, if you do either one of those things, you have something that's not a linear transformation. So let's do an example of that. And then we'll end the video. Show that t from another function from R2 to R2 given by t of x1, x2 equals 2x1 minus x2, x2 squared is not a linear transformation. Generally speaking, showing that something's not a linear transformation is easier than showing that something is a linear transformation, because all you need to do is you need to come up with a specific example. So what we need to do is we need to show either there's v1 and v2 such that you have this inequality, or there's a c and a v such that you have that inequality. Now you have your choice. It's possible, since we're given that this function is not a linear transformation, you know that you're going to be able to do one of those things, but you're not told which one. So the best thing to do is to just try to see if it's possible, for instance, for the first condition to not be true. So can you come up with v1 and v2 such that t of v1 plus v2 is not equal to t of v1 plus t of v2? Well, at this point, you sort of just have to try different vectors v1 and v2. So let's try, and you just make up some random vector. Okay, so let's try v1 to be 1, 1, and v2 to be 1, 2. Okay, those are vectors in R2. Now let's calculate the left-hand side, t of v1 plus v2, and let's calculate the right-hand side, t of v1 plus t of v2, and hope that they're not the same. Well, then, what's t of v1? T of v1 is, you plug in 1, 1, so you're going to get 2 times 1 minus 1 comma 1 squared, and that's going to be 1 comma 1. So that's t of v1. And t of v2 is going to be what you get when you plug in 1 and 2. That's 2 times 1 minus 2 comma 2 squared, and that's going to give you 0 comma 4. So in this case, t of v1 plus t of v2 is going to equal 1, 1 plus 0, 4. That's 1, 5. Okay. Now what about t of v1 plus v2? Well, also t of v1 plus v2 equals t of, so v1 plus v2 is going to be 2 comma 3, right? Because you just add v1 and v2, and then when you plug that in to your t, you're going to get 2 times 2 minus 3 comma 3 squared, and that's going to be 1 comma 9. So when you did t of v1 plus t of v2, you got 1, 5. When you did t of v1 plus v2, you got 1 comma 9. They're not the same. So since for this particular v1 and v2, t of v1 plus v2 is not equal to t of v1 plus t of v2, and you should write this down, you should write down which condition is not satisfied in the linear transformation. Since these are not equal, t is not a linear transformation. And that's your proof. Okay. That shows that t is not a linear transformation. Now, before we end, let me just make one final comment. So pretend that a student writes the following. Okay. So I'm going to make up something. So let's say you want to show that t does satisfy this first property. We showed that t doesn't satisfy the first property of being a linear transformation. But let's say a student does this. Let's say a student picks v1 is 2, 0, and v2 is 3, 1. Okay? And then they calculate t of v1. Well, what's t of v1? That's, where's the formula? 2x1 minus x2. Okay, so that's going to be 2 times 2 minus 0, comma 0 squared, and they get 4, 0. And then they calculate t of v2. That's going to be 2 times 3 minus 1, comma 1 squared. That's going to be 5, comma 1. So then when you add t of v1 plus t of v2, you're going to get 9, comma 1. Now if you do it the other way, which is t of v1 plus v2, okay, v1 plus v2 is going to be 5, comma 1. If you plug that in, you get 9, comma 1. And now the student says, hey, look, these two are the same. So since t of v1 plus v2 equals t of v1 plus t of v2, condition 1 is condition 1 in the definition of a linear transformation is satisfied. Now what's wrong with the reasoning? There's no arithmetic mistakes. But what's the issue? The issue is that it is true that for this particular v1 and v2, the left-hand side matches the right-hand side. But that doesn't mean that it's always true, no matter what your v1 and v2 was. It was just a coincidence that for these particular v1 and v2, the equation holds. I mean, the condition, when you read what the actual conditions are, okay, don't just pay attention to the equation. The condition, the first condition is that for all v1 and v2 in Rn, the right-hand side is true. That's the whole property 1. This is saying that every single time the left-hand side equals the right-hand side. Okay. It doesn't mean sometimes the left-hand side equals the right-hand side. So if you test this v1 and v2 and you get that they're equal, that doesn't mean that it's equal every single time. So that's the reason why this is not valid. It is true that for this v1 and v2, t of v1 plus v2 equals t of v1 plus t of v2, but that does not mean that condition 1 is satisfied. Condition 1 says that it needs to be true no matter what your v1 and v2 are. And that's why when we did our proof that this function is a linear transformation, we didn't plug in specific v1s and v2s. We worked with a general v1 and v2. And we showed that no matter what your x1, x2 are, no matter what the components y1 and y2 are, t of v1 plus v2 okay, is always going to equal T of V1 plus T of V2. That's why for this proof that something works for all V1 and V2, you had to work with the general V1 and V2 with general symbols instead of specific numbers. But when it came to finding a counterexample to show that something's not a linear transformation, then you are allowed to use specific V1 and V2. You just need to find one specific V1 and V2 that makes the left-hand side not be the right-hand side. Okay, so that's what I wanted to say. That's like an introduction to what a linear transformation is, but we'll talk more about general properties of linear transformations in a later video. Thanks for watching.